Jai Hind everyone. My name is Pooja Pandey and I'm the assistant professor in the MC department in Ajay Kumar Garg Engineering College. And today I'm going to discuss a very important part in which students face some difficulties to understand that how we are going to solve or how we are going to understand that problem. So I'm going to discuss the software solution to the critical section problem, and in that in this presentation I'm going to discuss the Dekkers algorithm. But before studying about the software solution to the critical section problem, I am going to just give a recap of actually what is a critical section problem and what are the requirements to fulfill its solution, right? So after this presentation, the students, you all will be able to understand that what you mean by the critical section problem, and you will also be able to understand, I hope, that what are the three requirements for the critical section problem to solve the problem. Then I'm going to discuss about that what do you mean by the Dekkers algorithm and how the process works in the Dekkers algorithm. Then I'm going to discuss the how Dekker satisfied all three conditions, which are the finally the solution for the critical section problem. Okay. Now, the first thing is that what do you mean by the critical section, and this is a very important part, and in daily life we encounter this problem, but we never give a glance on that problem. So just if I'm going to discuss about the definition, that what do you mean by the critical section problem, it is nothing. It is, you can say, a critical section is mainly a part of a program where we normally share the data which is going to access, okay, where shared data is accessed. In the critical section, the condition is that only one program will execute or only one process will execute at a time, right? And if suppose that if multiple processes are wanted to enter together in that critical section, then it will lead to the data consistencies. The whole sole summary of the critical section is that we have to understand that critical section is a part of the program where the shared data is exist. Only this, the critical section, okay, where the shared resources or shared data are exist, that is known as a critical section. Okay. Now, and how does it works? When we are talking about that how the critical section works, see, when a process enters the critical section, and mainly the critical section is a part of the code where we are accessing the shared data. It asks the permission before accessing the data. It doesn't mean that anyone will come and access the data. No, you have to take the permission. So that's why what we are saying, that when a process before entering the critical section, they have to take the permission and the protocol that ensures only one process, the protocol, okay, that this you have understood that it must ask the permission. Now, permission we are taking, okay. Now there is a protocol in the critical section which ensures that only one process will enter in the critical section at any given time, and that process is known as the mutual exclusion. That is a basic property of the critical section solution. So for example, if I take an analogy or if I take a real-time example for the critical section problem, then it means that imagine if you want to write something in the same notebook. If two people are writing something in the same notebook, to avoid that problem, to avoid the writing at the same time, how will they agree? They will request the permission before writing to each of them, right? They are taking the permission. Now, if one writer is writing, let us suppose writer X is writing, then letter Y is waiting for it. So that is a solution for that, right? So it will, and after the process X, or you can say writer X has completed the writing, it will leave the signal that yes, I have completed the writing. Now it is your turn. So that is exactly what the critical section protocol does for the process. But we find a problem when multiple processes want to enter the critical sections at the same time. Then there can be a situation that we will face the problem, right? Now, what is a problem? Before I have already discussed that what is the problem, that if multiple processes are entering the critical section at the same time, the chaos will be there. What will be it will lead to? It will lead to the data consistencies and the data corruption. Okay. Now, to prevent this process or to prevent the problem, what I am going to do, I am just taking a protocol. It will provide a permission to the process that okay, now this process P1, or you can say process X, is going to enter in the critical section. Now this whole process is known as your mutual exclusion. Now this is a first basic property for the solution of the critical section problem. Now, there are other two properties also for the critical section problem, that we should satisfy all three requirements. Then only we will find the critical section problem solution. Unless if we are not able to find out all three requirements, we are not able to satisfy the all three requirements, then there will be a problem. Then there will be a problem of the data corruption and the inconsistencies. Okay, so this we have to understand very clearly, that what do you mean by the critical section problem, and what the problem we are facing when we are our code is entering or our process is entering in the critical section. Okay, it is known. You have to understand that what do you mean by the critical section. It is a part of the code. Okay, it is a part of the code where we normally access the shared data, and if multiple processes are, that will be known as a critical section. Till now you have to keep in mind that. Now when multiple processes are going to enter in that process, in that critical section, a problem will be rose. That is the critical section problem. To solve that problem, critical section problem, that they must satisfy the three requirements, in which first requirement is that the mutual exclusion problem, in which we say that only one process must be entered in the critical section at the time, right? And this property is called the mutual exclusion. Now, what these are the three requirements of the correct solution for the correct critical section problem. These three requirements, they should satisfy. The first one is mutual exclusion, second is your progress, and third is your bounded waiting. Mutual exclusion, I have already explained you that what is a mutual exclusion. At a time, only one process, mutually only one process will enter in the critical section. For example, if I take an example of a bank system, when we go and check our locker, only one customer whose locker is there, who wanted to check that locker, only that customer is going to enter in that locker, and even the bank employee and the other customer will be out. So that is a mutual exclusion, right? That is a mutual exclusion, we will say. Now, when we are talking about the progress here, it means that it means mainly we will say that it will be a development. But when we are discussing about the critical section, when we are discussing about the correct solution of the critical section, then we will find out that progress means that we don't have to keep our CPU or our system ideally, right? For example, when we are going, I'm taking again an analogy for that. For example, when we are visiting to a doctor, we normally take the appointment. For a moment, if we are late by 10 minutes or 5 minutes, what the doctor assistants will do, it will just allow the other patient who has come earlier to go inside the cabin of the doctor. Okay, so that is what it means, that if the process is not available, then the next process which is available in the system, it will be allowed to enter in the critical section part. That means that we will continue our process. It doesn't mean that we have to wait for the process P1. If process P2 has arrived earlier, then it will be follow that rule. Okay. Here you can understand that there are two types of the solutions, or you can say there are two types we normally use, here I will take a part, that we normally use a word in the operating system, that is your primitive and non-primitive, right? Here primitive, what do you mean by the primitive? Here primitive means that normally if a process has started the work and suddenly some interrupt has come, then the process X will stop there, wait there, and then when the interrupt will be cleared, the process process X will start from that part only where it has stopped it work. So that is a primitive mode. Now when we are discussing about the non-primitive, it means that when a process has started to do the work, it will be stop until it will be stopped when that process when that work has been completed till end. It will not break in that part. Okay, so keeping in this mind the primitive and the non-primitive, you can understand the progress. If I am taking the example of the doctor's clinic, that the patient is going to the doctor, and if he or she is late by 5 or 10 minutes, then what will we do? We will allow other patient who has come earlier to go and visit the doctor. Now when the process P1 or process X, or you can say that when the patient X who has come late, when he will arrive, then he will have to wait and go. So that is what the requirement of the correct solution, and it means that we are not keeping our CPU ideal, right? Now when I am talking about the bounded waiting, it means that we are allowing the process in such a way that each process will be able to access the resources equally. Equally it will have to access the resources. So that is what the meaning of the bounded waiting. It means that for each process we are going to keep the limit, so that how each process will get the get the permission to access that resources. So these are the three requirements of the correct solution, or you say the three requirements for the critical section. Okay, for solving the critical section problem, these three requirements must be satisfied. Now need for the software solution. Why the software? See, there are two types of the solutions, the hardware and the software. But why we need the software solution? Initially, we need the software solution because initially when we were finding out the solution for the critical section, there were no hardware solution were available. If no hardware solution were available, then there was a no test and set instructions were available, right? So we need a logical solution for that. That's why we need the software solution to solve the critical section problem. And for this, we always assume that there are two processes, P0 and P1, and they are sharing, and the sharing memory is available. See, sharing memory is available, it means the critical section is there. Okay, because the shared data has been accessed in the critical section, that is the critical section. Okay, now software solution to the critical section. See, I am going to take the critical section, I am going to discuss the critical section solution, both the algorithms, but in the different videos. In this video, I have discussed the critical section problem. What do you mean by the critical section, and what do you mean by the you can say the what are the requirements for the critical section. Now I am going to discuss the first part of the software solution to the critical section problem. Now there are several algorithmic solution that solve the critical section problem without requiring any hardware support. In this, when we are discussing about the software solution, we have to keep in mind that we doesn't require any hardware support. Okay, now there are two solutions. First one is your Dekker solution, and second one is your B.Tech solution, which we are going to discuss in the second my second video lecture. Okay, now for the Dekker solution, what we are going to do, that we have to understand that, see, Dekker solution is one of the most earliest software solution. It was the first most solution what we have find out that for the software solution of the critical section. Okay, and it was designed mainly, it was designed for the two process. This we have to keep in mind that Dekker solution was normally was designed for the two process, which ensures that there is a mutual exclusion and there is a no starvation. No starvation. Starvation, what do you mean by the starvation here? Starvation means that if one process is keep on using the resources for a longer time, other process we have to wait for a longer time, and that means that waiting time has been increased more. So that means that there is a starvation for the next process. So when we are talking about the Dekker solution ensures that there is a condition of the mutual exclusion and there is a condition that there will be no starvation between the for the any one of the process. It means that each process will get the fair turn. In the Dekker solution, we normally use the flag. We are discussing about the two process, so we are taking the two flags. Flag means that it shows to enter the code. Okay, it shows to enter the row. Flag means it is raising. The process is raising his hand and it's saying, okay, I want to enter. Just you are showing your interest that you wanted to enter that program, right? Now, what does the turn means? Turn here means that it decide which process will we go inside the critical section. So we are using these two variables for it for the Dekker solution, right? Now here you see it's many students get afraid of this code, but it is a very simple code. Let me explain in a very simple language that normally we are taking the when we are discussing about the Dekker's algorithm, it means we are discussing about the two process. Here what I have taken two process Pi and Pj. Okay, now first understand how we are doing, then we will understand the working of it. Here what I am going to take, we are taking the two process, right? That is P1, Pi and Pj. Now very clearly if you see that here what I am seeing, okay, I am standing here. Here very clearly you will see that here this flag of I is equals to true. What does it mean? It means that process Pi, first process, has raised, it is saying that I wanted to enter in the process. Same time, in that same time, again next process that is process Pj, it says that okay, I also wanted at the same time. That is what the processes start, process Pi and process Pj. Two processes are at the same time they wanted to enter in the critical section. Okay, you have understood that. Now what I am going to do, we are taking that, now we are checking if while flag of j, it means that I wanted to enter in the process, but next process is saying that he is waiting that okay, okay, you can go, other process can take the turn, right? This for Hindi we say that pehle aap. Okay, so that's what I mean to say, that flag I have has given that I wanted to enter. Here flag j has given that I wanted to enter, but even though the flag I has given the thing that I wanted to enter, he is allowing, he is saying that okay, next process that is flag j, this process j can enter in the, if he wanted to enter, if he wanted to enter at the first position, okay, he is giving up the permission, right? Now here also what does it mean? In the second part, if flag of j is equals to true, again he wanted to enter, but again he is checking that whether the other processes wanted to enter or not. If other process too wanted to enter in that critical section, then he is giving the, again he is giving the turn to the other process. Okay, now here what does it mean? If turn is equals to j, it means that if turn is equals to j, here what I have done, that I have given the entry to the second process, that is flag j process, And again, if turn is equals to j, it means turn, whose turn is there? Turn is for the next process, that is j. Okay, now here you again understand. Here flag of I have given, even though the flag of j has said that I wanted to enter, but he has given the permission to the other process, and if other process is entering the process, then it means that whose turn is that? Turn is process pi, right? Now here if you come in this code, that if this process is are true, it means that flag of j is there, and turn whose turn is there? Turn is process next process, that is process j. It means that flag of I is equals to false. It means that this is not using the resources. This is not entering. That's why we have shown that flag of I is false. Why? Because here flag of j has been entered and turn has been given to the next process. That's why the previous process has said that it is false. It is not accessing the resources. Now, and when it will be take this till which time, or you will say which steps it will execute like this, till the turn is equals to j. Now turn is equals to j. If turn is equals to j, it will take all these steps will be executed till turn is equals to j. Now when it is completed, it means that flag of I is equals to true. Now if flag of I is equals to true, it means that permission has been given to the next process, that is flag I, process I. It means that it is entering to the critical section. Then again the then the process has been completed, or you say the process pi has been completed. Now this again whose turn will be there? Turn is equals to j. Next process will execute, and again the when turn is j, the flag of I or the process I will be false. Then the remaining process. So what you have to understand, that you have to understand, if both the flag are raising at the same time, it means that they have to ask to the other process if they wanted to enter in the process or not. If they are entering, they are lowering their flag. Okay, so that is mean. Now one more point you have to keep in mind in this, that when this process is entering this you say the flag of I, this process pi is entering. Let us suppose that if I am saying this condition is not satisfied, okay, if I am saying this condition is not satisfied, it means that, or how this condition, for example, both the process has been has raised the flag at the same time. Now suppose that if flag j has not has been delayed by 2 seconds or the 3 seconds, what does it will do? It the flag, then it is not going to ask from the flag j. The flag I, the process pi, will directly enter into the critical section and it will process accordingly to that. So that is what your Dekkers problem, right? Now, and now how Dekkers, we have understood the pseudo code. Now how Dekkers satisfy the requirement? Dekkers, according to that, again I am saying for the critical section there are 3 parts, right? It means that mutual exclusion. In the previous pseudo code you have seen that both cannot enter together because of the while condition. We are using the while condition, and it means that both cannot enter the condition together. It means it is satisfying the mutual exclusion. Now if I am talking about the second solution requirement of the critical section, it means that progress. And what does the progress means? That if no one is inside, other will enter. Now remember the point that when both the process, one of the process has been delayed by some time, the other process is not waiting, and that process is entering directly. So that it means that if no one is inside, then one can the process which is available, it will enter in the critical section. Now it means that it is satisfying the third requirement of the critical section. Now when I am talking about the bonding waiting, it means that it is providing the turn. Okay, it is limiting the turn that, okay, now process P0 is entering in the critical section, and when the turn of the P0 has been completed or turn of the PI has been completed, then process PJ will be there. So we will find out that each process is getting the equal time. So it means that there is no starvation. So that is how the Dekker satisfy the requirement. Now, but there are a limitation of the Dekker's algorithm, because it only works for the two process, and it has got the complex logic. Because if you see that we are using the do while loop, and we are checking if turn is equals to if process if there are two process PI and PJ. If process PI has raised the flag, whether process PJ is entering or not. So this logic is very complex, and it is very complex to for a person to understand, or if some point has been missed in while loop or something, then there will be a complex thing. Now it is very difficult to implement because the logic is difficult. So logic is complex, so it will be a we will find difficulty to implement this solution. So mainly it is a theoretical importance, and because of all these four parts, we find out that these are the limitations for the Dekker's algorithm. And to overcome all these limitations, we are going to discuss Peterson's solution in the next video lecture. And till that, we will wait, and thank you all. Jai Hind.